Hello, everyone, and welcome to Sedimentary Rocks. So, sort of the way we talked about magma generation when we talked about igneous rocks, we need to kind of begin a little bit talking about sediment and where sediment comes from, because obviously sediment, or small pieces of rock or mineral, are going to play a large role in sedimentary rocks. And in fact, sediments in geology are kind of their own thing. If you want to be a geologist when you grow up, you're going to take a whole class in sedimentology, which is just the study of sediments, and it is surprisingly mathematical and quantitative. For example, if you study beaches, you're going to be all about sediments without worrying too much about rocks. And so sediments are kind of their own thing. And so we want to take just a couple minutes here to talk about where they come from. And so, we'll also talk about sediments as a thing. Separate from sedimentary rocks. There's a couple words that we use, and we want to make sure we get them. If I can get to the next slide, there we go. Weathering and erosion, and a lot of times these words are kind of used almost as if they mean the same thing, but they don't. They happen kind of at the same time, but they don't mean the same thing. So weathering is breaking rock down, right? You've got a rock sitting out somewhere and it gets broken down. There's two different kinds of ways to do this: physical and chemical. Physical weathering is pretty easy to understand. You're turning big rock into little rock, right? Rock has, plants growing in it that physically break it apart. You can frost wedge it if you get water in cracks. Rock out just sitting outside is going to physically break down. But the other thing is chemical weathering, right? And this is particularly important maybe in Florida. Chemical weathering is, as the name implies, chemically breaking rock down. And there's a number of different ways to do this. There's things like hydrolysis and all kinds of fancy ways to do this, okay? But, basically what we're talking about here is, something like dissolving the rock, right? And this is important in Florida because, sinkholes, right? We have a bedrock made of limestone, and that bedrock is subject to dissolution when you run groundwater through it that's even a little bit acidic. And so, we have our, pine trees and whatnot, and those pine needles make the water kind of acidic as the groundwater runs through them. When you look at rivers in Florida, a lot of times they're kind of brown. That's not mud or something, that's tannic acid. And so when that water runs through the bedrock. Let me say it again. When the groundwater runs through the bedrock, it dissolves it, making springs and caves, and if a cave collapses, a sinkhole. So we worry a lot about chemical weathering here in Florida. And then the other thing to keep in mind, because remember from igneous rocks, we talked about Bowen's reaction series, and I said, look, this is something that geologists just come back to over and over again. And sure enough, when we think about weathering, minerals that are more mafic are higher up on Bowen's reaction series. That would be olivine, pyroxene, calcium-rich plagioclase, feldspar, things like that. Those tend to be way more susceptible to both chemical and physical weathering, whereas things like quartz or maybe the feldspars or the sodium plagioclase are more durable. They're less susceptible to chemical and physical weathering. So if weathering is breaking rock down, erosion is then moving that weathered material from one place to another. Now it's difficult to have one without the other. It's difficult to continue weathering if you don't ever move the weathered materials off. And obviously, if it doesn't weather, there's nothing to erode. Okay, but there are weird cases where things happen in weird ways and things like that. And my phone is vibrating. I need to stop that. But So erosion is just moving that weathered material. Now we commonly think about moving sand or something like that down a river, and that's definitely one way to do it. But we could also move a what we call a dissolved load, right? If we dissolve something in water and give it enough time, water will dissolve anything. If we dissolve something in water, then it's going to get moved along, in solution, right? What we think of as fresh water is rarely actually fresh. There's almost always something dissolved in that water. So we can see here. This is Half Dome out in Yosemite, and we can see how it's breaking in these planes, in these flat slabs. This is called exfoliation, and this is a great example of physical weathering. Right, we're turning a big rock into smaller rock. This is something that igneous rocks frequently do. Stone Mountain does it too. When you expose them and you unload them, they expand and they exfoliate. They you get these sheets, these slabs of smaller rock that can break loose and slide down and actually be a bit dangerous if you're not careful. So this is a great example of weathering. And then if we just look at a random kind of muddy stream, we can see erosion, right? We can tell from the color of this that it's carrying a lot of sediment, but not just sediment that you can see, but then also that what we call dissolved load, right? That all of that stuff that water has dissolved. And let's talk about that for just a second. Let me go back here to give myself a little bit of room to write a couple of things. So water, given enough time, will dissolve anything. And let's think for a second about why that is. So when we think about water, and let me find my pen. I just got to do it up here. That'll be a better spot. Where's my pen? There it is. Okay. So if we think about water, we like to think of the chemical formula for water, sorry, I can't write, as being H2O, which is what everyone knows. But it might be a little bit better to think of the chemical formula for water like this. Hydrogen hydroxide. It's the same thing, right? We've got two hydrogens and one oxygen, but this gives us a little bit better idea about the structure of water. It's a hydrogen ion tacked onto a hydroxide radical, okay, and this will break apart. There is a dissociation constant in water where you will have free hydrogen floating around and also free hydroxide floating around. And so what this means, though, is that this hydrogen is an acid, right? If we think about other acids, and I D, hold on, I can't write that. Okay, ACID. There we go. This is an acid, right? If we think about other acids, HCl, sulfuric acid, H2SO4, hydrofluoric acid, HF, right? They all have that hydrogen on the front of them. And so this is an acid. Well, this is a base. So while water has a perfectly neutral pH if it's pure, it doesn't have a neutral pH because it's neutral. It has a neutral pH because it has an equal amount of acid and base. And so what does this mean? Well, what this means is if something will dissolve in an acid, it'll dissolve in water. If something will dissolve in a base, it will dissolve in water. And so given enough time, water will dissolve anything. And we're geologists, we have plenty of time, okay? And if you heat the water, it'll dissolve anything faster. So water is everywhere, and so you do a lot of chemical weathering. It doesn't need to be acidic water, it doesn't need to be fancy water, it doesn't need to be anything other than water. Water will dissolve anything. It's why it's a great cleaning agent, right? We wash our dishes with soap and stuff, but you can get by with just water because it will take that food off. And and if if you leave your pots and pans overnight or something, let the water soak for a bit, and it'll break things down, and then you can wash your dishes. So water is everywhere, and water will dissolve anything if you give it enough time. And if it's hot, it'll do it even faster. So don't discount that chemical weathering. It's definitely a thing. You might think that water. Oh, look at that! It kept my stuff. You might think that water is fresh, but it's not. It's not at all fresh. And so, well, no, it is somewhat fresh. Sorry, I'm trying to get my eraser going here. It's somewhat fresh, but even the freshest water in nature has some dissolved load in it. And when we talk about evaporites and things like that, we will talk about that. And I'm going to get rid of all this stuff so that it doesn't carry on onto my other slides, which is kind of weird. I wonder why it did that. And so weathering, let me just recap. Weathering is breaking stuff down. Erosion is moving it from one place to another, right? And so when we talk, for example, about beach erosion, that's really what we're talking about, is that sediment on that beach moving. Okay, so we know how to make, we're talking about making sediment. So how do we make sedimentary rock? Well, first of all, you are going to have weathering. You are initially going to have to break stuff down. Okay, physical and chemical weathering, and that is almost always followed by erosion. They could be solid particles that are made by physical weathering, or they could be a dissolved load made by chemical weathering. Now, at some point, you're going to need to deposit this stuff, right? You're going to need to either get those solid particles to settle out, which will make a what we're going to call a clastic sedimentary rock, or you need that dissolved material to precipitate, right? The word precipitate, that is the opposite of dissolve, right? So if something is going from a solid to suspended in solution, to individual molecules floating in that water, that's dissolution, right? The opposite of that, taking those individual solid molecules and bringing them back together, that's precipitation, right? And so, for example, I'll draw again. If I have, let's do a very common one, right? And so I've got calcium floating in the water, and I've got carbonate floating in the water. CO3. I can't write this. And this drawing pad makes it even worse. So I've got calcium floating in the water. I've got carbonate floating in the water. Under the right chemical conditions, I will bring these together, right, to make either calcite or limestone, depending on if it has a crystal form or not, right? And and there's lots of things that do this. We could do this with silicon and oxygen. We could do this with sodium and chlorine. We could do this with all kinds of things, right? There's all kinds of stuff floating around in that water, especially seawater. Oh my gosh. Seawater has all kinds of stuff floating around in it. And so if we get that to precipitate, we're going to make what we call a chemical sedimentary rock. And so there has to be some deposition. And then here's the other trick, especially if it is solid stuff, sand or something like that. You can't just deposit sand and make a sandstone. Okay, there's another step that has to happen there. You have to cement those sand particles together. Okay, pressure. It's because there's this idea out there. Well, if I just deposit a sediment and then I apply enough pressure, that will cause it to stick together. Probably not. Okay, especially not if it's sand. And so there is going to need to be some kind of cementation going on. Okay, common cementing agents are silica, SiO2, because it's just so common in the environment. But also another common cementing agent is calcium carbonate, which would be limestone if it was a rock, or it would be calcite if it was a mineral, or sometimes you just get ooze of calcium carbonate cementing the particles together. Iron is another common cement. Clay will cement itself. Clay particles are so small, they have a positive and a negative side, so they kind of cement themselves and can cement other things too. So there's a number of things out there that serve as cement. And then that last word, diagenesis, is not a word that you're used to seeing, I doubt. where metamorphism, which we'll talk about when we talk about metamorphic rocks, is high temperature, high pressure alteration of rock. Diagenesis is low temperature, low pressure alteration of rock. So you can't expect a sedimentary rock to sit around for millions of years and not have something happen to it. Maybe you replace the cement, maybe you dole. I mean, there's just all kinds of low temperature, low pressure things that can happen to sedimentary rock, or it could be exposed to high pressure and high temperature, and that'll be what we talk about next time, which will be metamorphism. But diagenesis is kind of the low pressure, low temperature version, if you will, of metamorphism. And so, so that is roughly how we make sedimentary rock, right? First, you need to make sediment by weathering a larger rock somewhere, then erosion, moving that weathered material. At some point, you have to stop moving the weathered material. That's deposition. And then you're going to need to cement it one way or another. And if it sits around long enough, it will be altered through various and sundry diagenetic processes that we're not going to talk about, but they are definitely there. So this process produces three different kinds of sedimentary rock. Detrital, chemical, and organic. And so these are these categories. I'm not a huge fan of categories sometimes because some limestones are kind of more detrital than they are chemical, and some people even call them organic if they're made out of enough shell. And so there's a lot of wiggle room here with these different kinds of sedimentary rock, and we're going to go into them in more detail here in just a little bit. But let's keep our attention on sediments. Because there's some interesting stuff to be done here. When we think about sediments, and when we think about sedimentary rocks, the thing that we learn from sedimentary rock is environment of deposition, right? Different environments make different sedimentary rocks, right? As we look at this drawing, and let me switch back to my pointer. As we look at this drawing, right, you're going to get one kind of sedimentary rock in a lake. Glaciers are going to produce a different kind of sedimentary rock. Rivers up in here will produce a particular kind of sedimentary rock. Rivers down here where they meander produce another kind of sedimentary rock. These deltaic regions produce another kind of sedimentary rock. As we move offshore, you'll get different kinds of sedimentary rock as you move offshore. Reefs make a particular kind of rock. Deserts and dunes make a particular kind of rock. If we have a little beach here, that's going to be a different kind of rock. And so if you know enough, you can work back, right? If someone hands you a rock, you can look at the sediment that makes the rock up and say, okay, this is maybe a beach sand, right? And you're standing in Wyoming. Okay, right. Now it gets interesting, right? Sea level clearly used to be a bit higher. And so this is really the point, where with igneous rocks, we learned that crystal size will let you talk about, where the rock formed, underground, above ground, and things like that. With sedimentary rocks, an examination of that sediment will tell you where that rock formed. And if that rock is millions and millions of years old, that environment where that rock formed might be different, and probably is different than the environment now. For example, if you go into the American Midwest, let's go to Michigan or Wisconsin or somewhere like that. Okay, or New England especially. Anywhere in the let me get it right. Anywhere in the eastern 2/3 of the United States, north of Long Island, north of New York City. Okay, all those sediments are glacial. Okay, you look at the sediments, and they are the kinds of sediments that glaciers make. And yet there are no glaciers anywhere near there, but there were, you know, 10, 15,000 years ago. And so, we can use these sediments to reconstruct what happened in the world. And so, in order to do that, in order to understand how we do that, we want to talk a little bit about the properties of sediments, and we call these bulk properties. And so let's take a look at them, because this gives us a good foundation for being able to pick up a sedimentary rock and describe it. And more importantly, say, okay, this sandstone, for example, formed in a desert. Okay, and so that is ultimately our goal here. And so, so what are these bulk properties? Well, some obvious ones. Size. Right? How big is the sediment? We have something that we measure this on called the Wentworth grain size scale, and we can see it here. Maybe the easiest way to think about it is the diameter of the grain size in millimeters. Okay, so up in here we have boulders, and yes, geologists really do have a literal size cutoff in millimeters for boulders, cobbles, pebbles, granules, sand, silt, and clay or mud. Okay, we actually do have numbers that we can point to say, look, if it's above 256 millimeters across, it's a boulder. If it's between 64 and 256 millimeters, it's a cobble. If it's between 4 and 64, it's a pebble. And I know, this is kind of silly because, we're all going, it's a boulder, but it's good to have numbers. It's good to have numbers. So this number right here is the number that sedimentologists actually use for this. It's called the phi scale, and it's got a rather arcane formula, but it's actually very useful for sedimentologists. And so for sedimentologists, phi, I cannot write, equals the opposite of the natural log of the diameter of the particle in millimeters. Right, and I know I'm gonna make a better fee there, but I know I'm probably stretching your algebra here, and that's fine. I'm not gonna make you calculate this. Don't worry. I'm just not. I even missed it that time. Oh well, I'm giving up. So anyway, I know I'm stretching your math here. Don't freak. Okay, but you're not going to have to do this or anything, but that's the formula. Okay, so you take the diameter, you take the natural log of the diameter, right? And so, and then you ask yourself, okay, what exponent do I use with the constant e, which is, I believe, 2.54. I'll have to look that up and make sure. Hold on, I'm going to pause the video and go look that up and make sure I'm not lying to you guys about what e. Okay, good thing I looked it up. It's 2.71. 2.71. So anyway, ask yourself, you remember how logarithms work. What number do I use with 2.71 that will give me that, as an exponent, that will give me that number, and then take the opposite of that. Okay, whatever, right? There's our little algebra review for the day. The reason that sedimentologists use the phi scale is because notice how it gives you really nice breaks between your size categories, right? You no longer have to, go 256. It's just -8, right? Or 64. It's just, it's just -6. And so we take the opposite because it makes it easier to graph things. Just trust me on this, it does. But anyway, and so now, the cutoff between sand and gravel is -1. The cutoff between sand and silt is 4. The cutoff between silt and mud is 8, right? And so it's kind of a pain in the neck transition to do, but it's worth it. In the end, it really is worth it. it makes things it just makes the numbers easier to work with and easier to graph and easier to deal with. My main point here, though, is that we really do have a very sophisticated way of measuring sizes. And I'm going to pause the video one more time and find a picture of some sediment sieves for you guys. I'll be right back. As I was putting this together, I was asking myself why I didn't have this to go before, and then I realized that this is something I usually do in front of you in class. I bring my sieves in, and I show you how we do this. So, how do we, quantify this? I mean, we've got a fancy formula for calculating phi, and but how do we quantify these numbers? How do we separate out the sand, by these numbers? Well, we use a set of sieves. And there it is. And sorry, everyone, something went sideways. Had to edit. So the way we do this is, you get a set of sieves, which are just these round brass cylinders with screen mesh in the bottom, and then you arrange them from coarsest to finest, and then you dump your sediment in there. Now, if you're unfortunate, you have to shake them by hand. If you're fortunate, you actually have a machine called a rotap that will rotate and tap your sieve set, or just shake your sieve set in this case, and it'll shake it, and it'll shake it for hours. Making sure that every bit of sediment works its way down through these sieves, and then what you'll end up with are these, samples of sediment of different sizes, and you weigh them, and you can get the size distribution of your sediment. And different environments have different size distributions. You'll see a different size distribution on a beach than you will in a desert, than you will in a river, etc., etc., etc. So this alone can be a very important technique for working out your environment of deposition. Is just the size distribution of the sediments. So what else do we have? Well, in addition to sediment size, there is sediment sorting. Now, sorting is the degree to which all of the sediment grains are the same size, right? So next time you go to the beach, pay a little bit of attention to the sand, and you will see that it's all sand, and it's all sand, that is about the same size. That is a very well sorted sediment. Okay, if you go up into the mountains, or maybe let's go into a glacial region. Okay, glacial sediments are unsorted. You have everything from boulders to silt-sized rock flour from that glacier, literally grinding up rocks underneath it. And so that's the difference, right? And so, we can look at this and we can see, like a rock, like a conglomerate or a breccia, right? That includes, pebble-sized particles, either rounded or angular, along with sand-sized particles and all kinds of other things. Or we could see this very well sorted sandstone, right? If I look at this close up under some magnification, we can see that all the sand grains are about the same size. Okay, so we use you can quantify this with your sieves. Right, your sieves, if it's sediment and not rock, your sieves will break this out for you. Right, if if I go back to this for a second, sorry, let me drink something here. If I go back to this for a second, we can see that if we dumped this sediment into that sieve set, we get a lot of different sizes there. That's a very poorly sorted sediment. If, on the other hand, we dumped a beach sand in there, you're probably just going to get this. Right, if you go to Clearwater and you pick up some sand and you dump it in a sieve set, go to Clearwater Beach, pick up some sand, dump it in a sieve set, you're not going to have the pebbles or smaller pebbles or granules. No, you're going to have different sizes of sand, right? That's a pretty well sorted sediment, okay? On the other hand, if I went up into the mountains, into a mountain stream, and I dumped a handful of sediment into a set, it would probably look something like this, right? Where I would have a few pebbles, a few smaller pebbles, some granules, some coarse sand, some fine sand, right? That's a very poorly sorted sediment. And so that's what we mean when we talk about sorting, is just, how much of that sediment is the same size, and your sieves will pull that out for you, right? That this is why sieves are so important, right? They tell us about the size of the sediment, but they also tell us about the size distribution of the sediment. And people who work in sediments, they have their sieve sets, and don't touch their sieve sets, because they're very sensitive about their sieve sets. So okay, so sorting, right? The degree to which all the sediments are the same size. Now, in addition to that, look here. Look at this rock, this conglomerate here, and then look at this breccia here. Okay, now as we'll learn, both of these have pebble-sized particles, but the difference is the conglomerate pebbles are rounded, right? The breccia pebbles are angular, and that is a thing. That is absolutely a thing. We call it angularity. Actually, we call it angularity. We also call it rounding. But either word will work. I believe that your book uses angularity, but if you see the word rounding, that's also a thing. Okay, and so that is the degree to which the corners have been removed, right? Because if you have something in an environment, the first thing that happens is these corners get rounded over, right? These corners get rounded over, right? And so you could have something that is, very, very angular, has a lot of corners on it, or maybe subangular, sub-rounded, or rounded. Okay, beach sands, like let me give this away, right? If I look at this beach sand, you can see that these particles are pretty dang rounded. Okay, you don't see a whole lot of corners on them. If we go back to our scale, these are probably sub-rounded to rounded, and we usually really do just use qualitative words for this. You can measure it, but oh my gosh, get a life. Usually we just, you do this enough, you learn what angular looks like, you learn what subangular looks like, you learn what sub-rounded looks like, and you learn what rounded looks like. You can go in, oh my gosh, you can go in and, measure the angles and do all kinds of weird things, but, if we just look at this, I think we can qualitatively say, yeah, these are, sub-rounded to rounded sand grains. And by the way, if we were looking at a desert sand, you can do away with the sub-rounded. It's very rounded. Looks like a whole bunch of little glass beads. Wind-driven sediments tend to do that. The other end of this, or the other aspect here, is sphericity, which is the degree to which the sediment grains look like a sphere. Okay, now that is not the same thing as rounded, right? And you can see here that if you have like a flat pebble-like thing, like you might find along the shores of a river, okay? If you have a flat pebble-like thing here, it could be very, very rounded, but not very spherical. Right, this would be spherical. This would not be spherical, but it would be rounded. And I know this is like, oh my gosh, but this is the kind of thing we worry about. Rounding usually happens first. And sphericity happens later, right? You only really see highly rounded and highly spherical sediments in environments where the sediment has been in the system for a very, very long time, right? If you've ever been to a river, especially one up north, you see a lot of these very rounded over pebbles that are not spherical, right? And so first, we tend to round things over, then they tend to break and turn into spheres, right? And so we talk about two different things here: rounding or angularity and sphericity. Okay, and so beach, once again, this beach sand is pretty dang, probably sub-rounded to rounded and pretty highly spherical too. I mean, these are not flat, right? And so this sediment has been in the system for a very long time. And so I'm talking around something here. When I say a sediment has been in the system for a long time, we actually have a word for that. And I've been sitting here for 5 minutes wishing I could say it. So excuse me. So let's get to it. Maturity, right? Sediment maturity. Is a sort of a qualitative measure of how long a sediment has been, in the quote unquote system. All right, from we will kind of begin this clock, if you will, at the point at which a sediment will break off from the rock it came from, and then how long has it been broken off from that rock. And so there's a way to measure this. So I'm at 36 minutes in this lecture. I'm gonna stop this. I want everyone to get up, walk around a little bit, get something to drink, go to the bathroom, don't read, or I don't know, if you want to, read a little bit, relax. Okay, take 5 minutes. I'm going to put up our Stone Mountain gristmill for 5 minutes, and then come back, and we'll go on. Okay, but right now I really want everyone to just take a break. I need one too. Okay, take a break. Back in 5. And we're back. Did you take a break? I know I did. I hope you did too. Okay, so we're talking about sediment maturity, which is just kind of a qualitative measurement of how long a sediment has been in the system. And immature sediments have not been in the system very long. They are physically very close to that source rock, right? That rock that the sediment originally broke off of. We call those sediments immature. They tend to be larger in size. They tend to be poorly sorted. They tend to be angular. They tend to be not spherical. And there tends to be a lot of minerals in them. You'll have a mixture of mafic and felsic minerals in them, right? Go to a mountain stream. Look at the sand in that stream, right? Or look at the sediment in that stream. And I'll show you here in just a minute, right? There's a lot of different stuff in there. It tends to be angular. It tends to not be rounded over. And there's a lot of different minerals and a lot of different things going on. Okay, mature sediments tend to be physically further from the source. And this is really easy for you guys in Florida. Go to the beach. Right? That sediment is smaller. It's usually sand incised. It's very well sorted. It's rounded. It's spherical. And it's mineralogically boring. It's mostly quartz. Right? If we went a little bit further up in the system, we might find some feldspar and some more felsic minerals. But a really, really mature sediment, like most, not all, beach sands, let's say in Florida, okay, are pretty much all quartz. There's some other stuff. There's some other stuff, but mostly quartz. Right? And so what this looks like in the environment is this, right? And so up here in the mountains, here I got a picture, right? You got these huge blocky cobbles to boulder sized sediment particles. I know it's weird to look at a rock and call it a sediment particle, but that's what we're doing. Okay, this is snow, by the way, you just know there's some sand down in there, some coarse sand down in there, right? There's just all kinds of different stuff. Mineralogically, it's very diverse. We could put a hand lens on that rock and find all kinds of different minerals in there and all kinds of different stuff, right? Whereas by the time maybe this very same sediment, kind of quote unquote, gets to the beach, and we've been looking at this picture a lot today, but looks like that, right? It's all quartz. It's all pretty dang rounded. It's pretty dang spherical, right? This is a very mature sediment. This is a very immature sediment. Okay, now, so we can, talk about different kinds of maturity, because maturity involves both. Let me actually go to this page. Sorry, guys. There we go. Because maturity involves both chemical and physical weathering, right? We can talk about two different kinds of maturity, right? We can talk about textural maturity, which is, size, rounding, sorting, sphericity, angularity, things like that, right? Because that is the result of physical weathering, right? That is the result of physically breaking that rock into sediment and then, altering that sediment physically as it remains in that system. And so we call that textural maturity, okay? But right, at the same time, that sediment is undergoing chemical weathering, right? The more mafic minerals are being broken down at a much faster rate than the felsic minerals are, right? And so that's a parallel but different process, right? Wherein we chemically break those sediments down. At the same time, we physically break the sediments down. Okay, so these two processes are separate, but they usually operate in parallel. Right? Almost always, as a rock becomes more texturally mature, it also becomes more mineralogically mature. Right? When you go to our sandy beaches in Florida, that sediment is both mineralogically and texturally mature. Okay, and that is usually the way that happens. Okay, but not always, right? You've been staring at a photograph of a black sand beach in Hawaii. And they have these in Hawaii. They also have them in Iceland. They have them in various places in the Pacific Ocean. And you know, that sand is black. In fact, here's what it looks like in a person's hand. That sand is black. Well, it's black because it's full of mafic minerals, right? And you know, and here is where source rock becomes important, right? This sand here is coming from that rock, or you know, the entire island is made of rock like that, which in Hawaii, oops, sorry, we'll get to that, which in Hawaii is basalt. That's all they got to work with, right? And so what you end up with is a sand that is texturally fairly mature. It's not very well sorted, but it's fairly mature, but is mineralogically immature, right? Because the only rock available is mafic rock, and so once the mafic rock goes away, there's not much left. And so there are cases, and these black sand beaches are one of them, where the textural maturity and the mineralogical maturity become uncoupled. They usually go together, but not always. And these black sand beaches are a great example of that. So now that we know a bit about sediments, let's talk about sedimentary rock. And so, remember that we have three kinds: detrital, chemical, and biochemical. And we could also call detrital sedimentary rocks clastic. And so and I need to check the notes and the review and everything, because I have a very bad habit of going back and forth between detrital and clastic. I really prefer clastic, but I suspect your book says detrital, which is why I wrote it that way on the slide. But just be aware that you'll see the words detrital and you'll see the words clastic, and they mean the same thing. Okay, and then so these are rocks that are, of course, made up of bits of sediment, right? Bits of other rock. And so what we're going to do is we're going to name them according to the size of the sediment, right? And so, as we know from our too detailed examination of the Wentworth grain size scale, that to a geologist, pebble, sand, silt, and clay are size categories. Do not go back and memorize the size cutoffs for these various things. Just don't do that, okay? It's not important, right? Your intuitive idea about what a pebble is will work just fine. Okay, and you've all been to the beach, you know what sand is. Silt is interesting. Silt is about the consistency of baking flour, and siltstone should really be one word. My apologies. And then clay. Clay is kind of interesting because clay is very fine. You cannot grind sediment into clay. You just can't. It was sediment. Things don't grind that fine. You have to chemically break things down to get clay. Clay is so small that it has a positive side and a negative side, and those things tend to stick to each other and stick to other things too. Which is why that famous Georgia red clay there in South Georgia, and for that matter North Florida, are famous for getting in your hair and getting on your clothes and never ever coming out, because it is now literally chemically bonded to your clothing. It can be a real pain in the neck. So anyway, so we name these according to grain size. And so if something is made up of pebble-sized particles, it's either a conglomerate or a breccia. A conglomerate looks like this. The pebbles are rounded. And then a breccia looks like this, right? Breccias are made of very immature sediment, right? But both conglomerates and breccias are immature, right? Because they're very poorly sorted. It's just the conglomerate's a little more rounded over. So the breccia is even less mature. Okay, because these fragments are angular, right? And so both have pebble-sized particles. The breccia, though, has angular pebble-sized particles, where the conglomerate has rounded pebble-sized particles. And we're going to come back to these and put them in a little bit more context, a little bit later on. And then if the rock is made of sand, we call it a sandstone. We've been looking at this for a while now. There are different kinds of sandstones. And we use a ternary diagram to classify them. If you go further in geology, you're going to learn about feldspathic sandstones and greywackies and all kinds of different sandstones. Sand is very, very common in the environment, and so sandstones are also very, very common in the environment, and so we subdivide them, and then also the bulk properties of the sand matter. Is the sand angular or rounded, or how well sorted is your sandstone? There's all kinds of other things that get subsumed into this sandstone. This word sandstone here is doing a lot of work. There are a lot of other sandstones out there in the world. And then with silt, for some reason, I stopped capitalizing the words and I turned it into two. I don't know what I was thinking. But anyway, siltstone, if you have a silt-sized particle, it makes a siltstone. And these, you can see some of it here, and we'll talk more about these layers of sediment here in just a little bit. I don't know if we'll get to it this one or in the second part of this lecture, but we'll talk more about that. And then also clay. If you have clay-sized particles, you make a rock called a shale. They kind of call all this mud, which kind of annoys me a little bit, but that's okay. And then silt makes a siltstone, clay makes a shale. Don't worry about mudstones. That's just another word for siltstone. So yeah. So so once again, we classify these sedimentary, these detrital. Sorry, I needed some tea there. We classify these detrital or clastic sedimentary rocks according to the size of the particle that makes them up. Chemical sedimentary rocks are, in the real world, a bit more complicated. They're not going to be here because I'm just going to show you some examples and we're just going to kind of move on. But if you do go further in geology and you're I don't know, drill logging or mapping or something, you're going to need to do a little bit better than this. Okay, but for now this will do. And so what's happening here is chemicals are precipitating out of water, usually seawater. Okay, seawater is a very complicated chemical solution. It has every element known in it in some quantity or another, and so it's not unusual at all for chemicals to precipitate out of the water. And so there's a number of them. I'm just giving you a couple of examples here. The first, and because we're in Florida, is limestone, which is calcium and carbonate precipitated out of the water. If it was a mineral, it would be calcite, but if it precipitates in such a way that it doesn't have a crystal form, it's limestone. Okay. Limestone is interesting. Limestone forms in warm seawater. Calcium carbonate precipitates out of warm water. That is strange, right? That is the opposite of everything else, right? Everything else dissolves in cold water and I'm sorry, I got that backwards, didn't I? Dissolves in warm water and precipitates in cold water, right? And we're all, maybe we're all Southerners, I don't know, but you make sweet tea, right? Or let's do it this way. Let's say you go to a restaurant and you order sweet tea, right? And you say to the waitress, "I'd like sweet tea," and the waitress says, "Well, we don't have sweet tea." Okay, you're probably not in the South. Maybe you're in New England, but the waitress says, "Well, we don't have sweet tea, but I'll bring you some unsweet tea and some sugar," right? That's not gonna work, is it? Okay, right? Because you and I both know you're gonna dump your sugar into that iced tea, and it's cold, and that you're gonna stir and stir and stir and stir, and it's not gonna dissolve. Okay, you're gonna get mildly sweet tea with a pile of sugar at the bottom of the glass, right? Things don't dissolve in cold water or cold tea, which is basically the same thing. And so every good Southerner knows that when you make your sweet tea, you add the sugar before you add the water, right? Or the ice, rather. Otherwise, it won't dissolve, right? Okay. Calcium carbonate is exactly the opposite. Calcium carbonate, for arcane chemical reasons that we won't worry about, dissolves in cold water and precipitates in warm water. Which is why Florida is covered with limestone, right? That limestone is remnant from a past time when Florida was covered with shallow, warm seawater that precipitates limestone like crazy. Okay, if you want to study this today, you go to the Bahamas, right? And where they still have that shallow, warm water, and you study the chemistry and physical properties of that water to understand how limestone precipitates out and forms. So it's odd stuff. 95% of the rock in Florida is limestone. The other 5% is chert. In fact, chert is everywhere, actually, a very common rock. It just kind of is, because it's silicon and oxygen, which are the two most common elements in the Earth's crust. And so it turns out that it's a very, very common rock. It has the same chemistry as quartz, in that it is silicon and oxygen, but once again, it's not quartz because it doesn't have a crystalline structure. Okay, a lot of times chert is cemented microorganisms. A lot of times, the chert is little tiny microscopic creepy crawlers that live in seawater and make a skeleton out of SiO2, and when they die, they end up cemented together to make chert. Chert is very, very common. If you become a geologist, people are going to bring you rocks all the time to identify, and they are almost always chert. It can be a lot of different colors. It can have a lot of different looks. But if you blindfolded me and said, "I'm about to put a rock in your hand, guess what it is now?" I would guess chert. It's very common. And so it also, though, either precipitates out of seawater, or it's a lot of these little cemented microorganisms together, or something like that. And then there's just flat out, straight out evaporites. These form from evaporated seawater, right? So seawater, has all of these chemicals in it, and so when you evaporate the water, you leave those chemicals behind. In fact, that's one way to make fresh water out of salt water, is to evaporate it and then recapture it. Okay, and you've probably seen this in quote unquote fresh water, right? If you put a pan of water from your faucet on the stove to boil, let's say you're going to make yourself some macaroni and cheese or something, and you forget about it. No, I've never done this, but you forget about it, and you boil that pan dry on your stove. Okay, look at it. There's this white gunk on the bottom of your pan. Okay, that white gunk was formerly dissolved in your water, in your quote unquote fresh water. There's almost, I mean, unless you're cooking with distilled water, and you're not, there's always going to be something in that water, and you might not be able to taste it. You might not even know it's there, but it's there, right? Well, if I evaporate seawater, just imagine the white gunk in the bottom of my pan now, right? And this happens naturally, right? This happens a lot, for example, in the Dead Sea region. And I'm going to pause 1 second and bring up Google Earth and show you. So hold on. Okay, so here we are in the Middle East. So here's the Mediterranean, Africa, the Arabian Peninsula down here, Europe up here, and over here is the Dead Sea. And so what we have here really is a very, very restricted basin, right, where there's a lot of evaporation out of here, and not a whole lot of rainfall, and not a whole lot of rivers running in here either. And so first of all, this water is very salty. But if we look at the edges of the Dead Sea, and there's a good spot right there. And actually, let's just look right up here. That's a cloud. so if we look here, here's a good spot. And so we look here, we can see along the edges of the Dead Sea, you can see this white stuff caked on here, right? That is evaporite. That is the leftover chemicals. We call them salts. Now, don't think NaCl salt, but these are the leftover chemicals, if you will, that are left over after the water evaporates. Once again, when you evaporate salty water, and oh my gosh, the Dead Sea is very salty, but once you evaporate salty water, you remove the water, you leave the salts behind. And I'm kind of putting air quotes around salts because it's not just NaCl, it's all the stuff that was in that seawater. And so this can leave behind a really interesting geological deposit. And let me get my PowerPoint back up and going for you here. And let me just do this, and this will pop it in for you can see everything. There we go. And so this evaporites lead to a very interesting salt deposit, or deposit called a salt dome, right? And this is kind of what one looks like in 3 dimensions. And so if you have an ancient ocean that dries up, it will leave behind this layer of salt, and that layer will flow and work its way upward into this kind of dome shape. And in fact, here's what it looks like with ground penetrating radar. Here's a salt dome, and you can see it working its way up and deforming the rock around it. And then once these salt domes, reach the ground surface, they look like that. And now you can mine it, right? Or you can mine it when it's still underground, but you can mine it, right? Salt is very not very, but it's valuable stuff. Maybe it used to be a lot more valuable back when you needed it to preserve meat and things like that, but we all put it on our French fries and use it as a seasoning. It used to be a necessary ingredient to make gunpowder. There were Civil War battles over salt mines in Louisiana because both sides needed the salt to preserve meat, but also to make gunpowder. And so this is actually an economic thing, right? These salt mines. And if I went back to Google Earth, and I'm not inclined to because I just don't want to mess with it, but actually, yes, I do. Hold on 1 second. Let's go back to Google Earth. Let me pause it. I'm going to go back to Google Earth and show you something. So looking back at Google Earth, if I zoom out and we go to the south of the Dead Sea, let me zoom out and come on, there we go. We see a sea salt operation, right? Cordon off the water, let it evaporate, scrape up the little bits, put them in a jar, and there you go, sea salt. Maybe by now you've realized that all salt is sea salt, right? Those salt domes I was showing you began their lives as sea salt. I'm going to go back to my PowerPoint, right? All salt is sea salt. It's just kind of a question of where it came from, right? This salt dome that expresses itself on the surface and then mine was originally sea salt. So yeah. I want to go back here and explain this picture. If you are a religious person, maybe you've read the story of Lot and his family fleeing the destruction of Sodom and Gomorrah. Or if you're a Christian religious person, although I think that story's in the Quran too. But anyway, as Lot and his wife flee the destruction of Sodom and Gomorrah, God says, "Don't look back, don't look back, don't look back," and Lot's wife looks back. And is turned into a pillar of salt. Right? There's a lot of salt in that region, right? Because the Dead Sea expands and contracts and expands and contracts with climate and things like that. There's a lot of salt in that region, and so there is one particular rock formation out there. Here it is here that people think looks like a woman looking back. I don't know. I don't see it. But they call this particular rock formation Lot's wife. After the story in the Christian Bible. It's I don't know. It's just kind of fun. But anyway, I've only got about 6 minutes or so left before I really want to stop talking, and so I think I'm going to go ahead. Actually, let me do this, and then that'll give us a good place to stop. So also, actually, no, I'm not, because I want to talk more about this. Sorry, guys. So anyway, I'm going to go ahead and stop now, and then we're going to pick up next time talking a bit about environments of deposition. But coal is my thing, and I don't want to rush it because I like coal, not to burn it to make electricity, but to study it as a scientist. So we'll pick up next time with coal, and then we'll move on into environments of deposition. Okay, I'm gonna go compile this, upload it, and I will see you all next time.